Good afternoon, everyone again. My name is Shuang from Harbin Studio Technology at Shenzhen. And so this topic is analytical algorithm-based position and rotation detection using a Tri-Axial Magnetoresistive sensor. So various capsule oscilloscope has been widely studied and used in the GI examination. However, it still has some problems such as the passive mode of motion and its uncontrollability. So the challenge of this technology is that how we can track and drive the capsule in the real time, and how we can improve the position and the rotation accuracy when we're tracking it. So currently, there are two kinds of methods that to track the various capsule and scope. Of course, it should be only one method, that is the magnetic tracking method, and it can be divided into two categories. The one is the permanent magnetic-based method, and the other is the electrical magnetic based method. The permanent magnetic-based method has a limitation of tracking range and the weak anti-interference ability. The electromagnetic based method uses one or more coils to sense the magnetic field to provide the position and rotation information. Also, the magnetic field can also be mirrored by the magnetic sensors. So here's our proposed method. We use uniaxial transmitting coils fed with the signals to provide the magnetic field, and use a Tri-Axial magnetic sensor to sense the magnetic field and provide the position and rotation information. Here we need to know that this is the planar method, and the magnetic sensor is moved in plan, and we here to provide the 3D position and rotation information, that is the 2D position xy and the rotation information theta. So the goal and advantages of this method is that we want to simplify the hardware structure of the electromagnetic tracking method by using the uniaxial transmitting coils and the Tri-Axial magnetic sensor. The magnetic sensor is small and it is standardized. And we also want to reduce the time consumption of the signal processing and computation. The localization parameters can be calculated by some simple and explicit analytical equations, and the parameters can be determined in a very short time, that is in only a single period. And we also want to improve the tracking accuracy, and our method has achieved average tracking error at 1.9 millimeters and 0.6 degrees. So before we introduce the algorithm, we have to calculate the sensor. First, the calculation includes the zero error compensation and the sensitive error compensation. After that, we can use the sampled signal to do the tracking method. So here's the magnetic model. We here use the magnetic dipole model to serve as the magnetic field model. Here in the figure, Bt is the constant related to the magnetic moment of the transmitting coil. P is the vector defining a spatial point with respect to the dipole. R theta and phi is a vector defining the direction of the dipole. I is current in the transmitting coil. S is the sectional area of the transmitting coil, and M is the magnetic dipole moment. So by defining the dipole's position as 0, 0, 0, and its rotation is denoted as MNP equals to 100, the magnetic field can be denoted as this equation So note that there are two sets of magnetic fields. One is the magnetic fields that parallels to the global tracking coordinate system, and the other set of magnetic fields is the signals that from the magnetic sensor. The relationship between these two sets can be seen at the bottom. That is is a rotation matrix. So here is how we can have the position of the sensor from the sampled magnetic field values from the sensor. So after we have the position information, we can then solve the equations as seen here to obtain the rotation information that is theta. So here is how our algorithm works. First, we sample the data from the magnetic sensor and then extract the signals by function fitting to divide the signals to two parts. First is the AC part and second is the DC part. We use the AC part to calculate the position information, and we use the DC part to calculate the rotation information. After as position and rotation information have been calculated, we finally have the 3D position and rotation as the position x, y, and z. So here is our experimental platform with signal conditioner and amplifier models to connect to the generator and the receiver to amplify the signals and to sample signals. We also use the Tri-Axial magnetic sensor to sample the magnetic field. The sensor is HMC 1043. We also use the uniaxial transmitting coils to generate the magnetic field. The transmitting coil is fed with sine signals. Also, we use a laptop to do the computation, and we use a 3D rotation stage to test the performance. So here is the position and rotation errors. The average total position error is about 2 millimeters, and the rotation error of half samples are less than 0.5 degrees. So here is the final errors. The RMS error of the position is 2 millimeters, and the rotation error, the RMS value is 0.7, and the mean error of the position is 1.9 millimeter, and the mean error of rotation is 0.6 degree. So here is the samples that we use to calculate the position and rotation error. Samples are distributed in a space of 10 centimeters plus 12 centimeters, and the localization values are close to the ground truth, as you can see in this figure. So in this work, we have proposed the electromagnetic tracking method, which is simple, fast, and applicable. In the future, we will improve the accuracy and especially the position error, and we also want to extend this tracking method to a full 6D tracking application. Okay, thank you very much.